Again, my name is Rick Sandberg. I'm a Senior Applications Engineer for Hawkridge Systems in our Portland, Oregon office. And as a panelist, I have Mr. Glenn White, who is our Simulation Product Manager. There just to make sure I keep in line and answer any questions for you. So, to open this up, I want to put SOLIDWORKS Plastics just in the context of all the other products in SOLIDWORKS. As most of you know, there's 3 levels of SOLIDWORKS with standard, professional, and premium. And premium comes with some simulation, both static and motion simulation. But then the baton kind of hands off, and after that we go into simulation professional, which gives us some things like frequency analysis and buckling, thermal, drop test, fatigue analysis, optimization. And then we have a 3rd level of simulation, which is into the nonlinear realm for materials and motions and harmonics, random vibrations, things like that. And then we also have our other simulation products, for instance, the flow simulation product, which also has a couple modules for specific industries. For instance, the electronic cooling module and the HVAC module. We also have a sustainability product that is there to help us calculate life cycle assessment. But today's presentation is all about the SOLIDWORKS Plastics tool, which has been with us several years now. It started out with the professional and premium levels, and we've actually added a new level as of last year that is being called advanced. Now, that's the current naming of the levels of this plastic product, although what's just been announced yesterday with SOLIDWORKS 2015, they will be renaming this to be a little more consistent with the way the other products are named. So we'll have standard, Plastics Standard, Plastics Professional, and Plastics Premium. And the Professional will now be called Standard, Premium will be called Professional, Advanced will be called Premium. I'm not going to worry about that right now. This was just announced, and that's coming in the next version, but we like to see consistency. So be aware that this is a separate product, a separate license, and it's an add-in to SOLIDWORKS. It works with SOLIDWORKS. So let's talk a little bit about why this tool exists. Why do designers and manufacturers need this tool? Historically, the whole molded part creation process has been a sequential one, starting with part design, and then you go to mold design, mold manufacture, and then into production and product launch. And whenever we have problems, the later in the process that this problem occurs, the more impact and the more cost involved, and more time being spent to correct it. So problems found at the later stage in the production or first article inspection can be very expensive to rework. And it can potentially go all the way back to being a part redesign. So what we propose with our SOLIDWORKS Plastic tool is to predict these problems early in the design stage, where it's much cheaper and much faster to remedy. So you're not going all the way into mold design and mold manufacture and even later before you find things like that. And that's really what this slide is trying to show, is that if you find problems back at the design stage, you can have a huge impact at very little cost. Whereas if you're finding a problem way late in the process, it's going to be a very expensive thing to try and deal with. And so if you can find that early, your return on investment can potentially be in the first project that you use the software. So that's really the goal. We're trying to bring together the whole design and mold simulation process into one seamless process and have a pretty high degree of confidence for your mold design just at the design stage. So simulation injection molding has some key capabilities to help us get there. We have a pretty extensive database of plastic materials, about 5,000 different plastics and materials shipped with the product, and it's being added to all the time. It's really designed as an analysis tool for designers. It has a pretty comprehensive range of analysis capabilities and results that we can see, but you really don't have to be a dedicated PhD analyst to be able to use this and interpret the results. It's really a very straightforward setup, and it's a guided process to do everything. So it's really quite straightforward and gives us really great, reliable results at the end. So we have actually these 3 different plastic packages. We have the Professional, Premium, and Advanced, offered, just introduced last year. And with the 3, it makes a very complete analysis package for plastics. I could discuss the various modules, but it's really best to show these modules in terms of who they're designed for. So in the Plastics Professional, it's really designed for the part designers, because we want the part designer to answer some basic questions. Will my part fill? Will there be weld lines or weak points in my plastic when it's all done? Are there any air traps that could be eliminated as part of the design process? And what we're really doing is simulating the mold filling stage. And we have the chance to then optimize our design for manufacture and determine if a gate location is going to solve some of our design issues. So let's take a look at our part in SOLIDWORks and see how this works. Again, this is an add-in. If I go to my add-ins command, it's an add-in that we can click on, SOLIDWORKS Plastics. And what I'm going to show in this presentation is the cover for a smoke alarm. This part has been designed in SOLIDWORks, so I've got a full feature tree to use and to be able to modify the part, but that's not essential in using plastics. We can actually run an analysis in plastics on any part that can open in SOLIDWORks. It doesn't have to be SOLIDWORks native. And if you're familiar with SOLIDWORks, you know that we have quite a few different types of files that we can open, 3D types of files. So everything from parasolids, IGES, STEP. It's really like a nice generic can opener of 3D CAD. We can open many different CAD formats and 3D formats. So if you can read it in with our open command in SOLIDWORks, you can run plastics analysis on it. So let's switch to another configuration and try running an actual analysis on this part. I'm going to switch to another view, and once we add in our plastics add-in, we get a new tab in the command manager, and we get a new tab over in our feature tree over on the left. To set up our analysis, there's really not that many steps. And like I was mentioning before, you don't have to be a high-level analyst to be able to do this, although the only analyst-type activity that we'll need to do is we do need to mesh this part. We have a couple different ways to mesh it, a solid or a shell, and it's really good to start out with a shell mesh. Shell is going to be much faster to analyze, much faster to mesh, but it won't be quite as accurate as a solid. But I think shell is a really good place to start when you're just first analyzing a part. And then as you get some results, you may want to go to a solid mesh to see things a little more accurately. Once we have told it to mesh, it analyzes our parts, and then it's going to come back and give us some information in terms of mesh size. The first one that we have is going to allow us to set different mesh for different bodies. If we have multi-body, it can handle that. We only have the one, so I'll click next and just go into mesh size setting. So we have a slider that we could use to set the different mesh size, but we can also type in a value. I'm going to type in a pretty good size mesh, which is going to be too big on purpose, and just hit the mesh to see what that looks like. And that indeed is going to be too coarse of a mesh for what we need, but it's okay to start with something like that because we can do local refinement. Either the set button to do manual setting of these refinements, or I can hit the auto button and set a graduation slider, hit mesh, and we can see that it's going to do a much more refined mesh for our part and be able to see a lot more detail in what's going on. So this should be sufficient for our mesh. And that's our first step of the process. Once we do that, we have our cavity that's defined for our project. And the rest of it that we need to set up is all about setting a material, setting an injection location or a gate location, and then a few fill settings. So let's first just take a look at setting a material. I can double click on polymer, and you can see I mentioned before that we have a pretty extensive database full of materials. And so we have a number of ways that we can go through and look for a different material. We can sort by family, we can sort by company. We also have a really nice find capability, search capability with a generic search field where I can type in any kind of parameter and do a search, or I can open up options and look on specific properties if there's just a particular property or set of properties that I'd like to find. Once I find my properties, I can pick from the list of what it's found. It will select it. You can see that I get a good number of properties associated with these materials. Hit OK. Now it's got my property set. I next need to assign an injection location. So double click that one. And this one's really going to be on a mesh node, but I'm going to just set it on the edge of this lip. You get a nice little icon that indicates where that's going to be. I'll accept that as my location. And now I have only one step left, fill settings for the basic professional analysis. I'll open up fill settings. You can see that it's giving me a filling time, melt temperature, mold temperature, and an injection pressure limit. So that's based on your machine. The melt temperature is going to be based on the material that's set, and I can uncheck auto and just give it. I know that I'm going to have a 2-second fill time. So I'll go with those basic settings, and that's really all that's needed to run this analysis. Now I'm going to just right-click on Flow, hit the Run Analysis, and once that starts, we get this Analysis Manager showing up, which gives us some really good, valuable information as it's processing, some intermediate steps. And you'll see that as it goes through and does each step, it's giving us a % completed, the processing time, and the maximum injection pressure at that point. So we get a lot of really nice, valuable information as it's processing, because if we see something that's amiss at some step during the process, we'll be able to just suspend it or cancel out of this, make our adjustment, come back, run it again. We don't have to wait until the entire study is finished processing. Nice capability to have that analysis manager there to show us the progress. Once this study is complete, we get this nice graphic of the fill process, and we get a whole set of results that we can look at. For flow, we have 16 different result types. You can see them showing up over on the left-hand side of my screen. And we'll also have some things outside of those result plots that we can toggle on and take a look at. Many of these are going to be quite relevant to the part designer, but also relevant to a mold maker as well. So we can already see that as this flows into my part, we've had, because of the thicker sections of my part, some of the mold racing around to the other side, and we're getting some flow fronts coming in on both sides of my ribs. So that may be a particular problem. We can also see where our plastic is filling up into an area where we would probably need to have some venting placed so that it has a place for trapped air to escape. And these are the types of things that we can really see quite well with this tool. All right, almost done, 90% complete. Last 10%, and then we'll take a look at some result plots. And there we go, we've got a complete result now. Our results, our manager closes up. We get our results pane on the left with our various reports or plots. And we also get a results advisor over on the right. The results advisor is a pretty handy tool because we have a general indication at the top with a stoplight, green, yellow, or red. Green means everything looks pretty good. Yellow would mean there's probably something that we need to take a look at and analyze a little bit more. Red means that we definitely have a problem and we'll have to deal with it. And then it goes into a little bit of discussion of some suggestions. It's saying that, you know, we've filled this with only about 66% or less than 66% of our maximum injection pressure limit. And so we may be able to decrease the thickness of the part and still be able to fill this, which would then decrease the cooling time and give us some added benefits beyond that. Now, of course, this isn't looking at, you know, things like structural integrity of the part, for thickness, or insulation, or any other design considerations. This is really just looking at, can you fill it into the mold? So let's take a look at this fill time plot. And the color is indicating the time. So we're just under our 2-second limit. We can also animate this with a play button down at the bottom left, and it will show that filling process, which we can loop or not loop. But what's even nicer is that I can actually dial back on these sliders the minimum and maximum position of my animation, and then dial it up with my arrow key on the keyboard one step at a time, so I can very carefully see how this is filling and what things might be impacted by how it's filling. So you can see again what we saw during the while I was completing that study, that we have some flow fronts coming together in the middle of these vent ribs, which is going to create weld lines and weak points in those ribs. And those ribs are already the thinnest part of my part and probably the weakest part. So we would like to try and avoid those weld lines if we can. We actually have a weld line toggle in this dialog box that I can toggle on and actually see where those weld lines are going to occur and see where the weak points would be in these ribs. We can also toggle on air traps. So it will indicate areas with these little purple dot spheres that indicate where air is going to be trapped. And there are different sizes based on the relative severity of the air trap. So all really excellent information to know as you're designing the part to try and avoid some things. Let's look at some other parameters. Pressure at end of fill. So we're only getting up to about 21 megapascals for our maximum pressure. And what you'll notice as I pick other result plots over on the left, my results advisor is updating to show us what amounts to an in-context help for each of those results. So as you're just learning the product and getting used to it, as you pick the different plots, we'll get an explanation of what those plots mean over in my advisor, which can be very helpful. So we can see things, I'm going to close the advisor for now, and we can see things like sink marks with thick areas of my part. We could get sink areas where the plastic will contract after it's cooled, and this will be an indication of where that's going to happen and generally how much. But we have much more accurate ways to see that with the upper levels of the product, and we'll see that as we get into that. But temperature growth at end of fill, cooling time is a big one. It's going to take us more than 58 seconds to cool this product when it comes out of the mold, and that's one of the largest time factors in all of this is how long is my cycle time, and that's a big factor. So that's some really valuable information right up front as I'm designing my part. How long is this going to take to cool, and how much impact is that going to have on the cycle time? So we can also see temperature at end of cooling. Since we have a lot of thick material, this is going to take a good bit of time to cool, and I'm going to have a pretty high temperature at the end of everything. We got a lot of thick material there. Shear, things like shear stress and shear rate are going to affect the any surface defects that might happen. We want to try and keep shear stress and shear rate at a lower value. But once we've seen our results, that's where we can go right back to our SOLIDWORKS part and make some modifications. Now the other nice thing about this is we can do this with configurations. So I've got some configurations saved with some changes to my part. Let's go to this next configuration, go to a 1 millimeter thickness, and I have already run the project. So it's asking me if I want to load this plastics project for this configuration and its results. Yes, let's do that. And you can see that I've got a much thinner wall on this part, and I've stiffened it with some ribs along the side. So let's see what the results look like for our plastics analysis of that version of my part. I'll load up these results, and here's my fill time. Look at that. At a little over 1 second, it actually stops filling. Why is that? Because it's hit the maximum pressure that I've allowed for this part. So the part is so thin that we're getting what's called a short shot. It's not filling all the way. Hugely important or valuable information to get as you're designing your part. I know that I can't really even fill this part with the way it is right now. I'll have to do something with it. I need to either change the material to something that will flow easier, change the part thickness again, make it a little thicker, or maybe, if I have the option, maybe go to a different machine that can produce a higher temperature or a higher pressure. But let's try another variation. And I have another configuration that I can use for my analysis. This one is, once again, a little bit different wall thickness. It's thicker again than that last one, but not as thick as the first one, so I'm still using some ribs. And let's take a look at the results of this part variation. In this case, fill time, right at 2 or 2.1 seconds. It's filling all the way, which is great. You can see that our pressure is around 44 megapascals at the end. Cooling time is dropped dramatically less than or about half the amount of cooling time. So we've gone from 58 seconds of cooling down to 27 seconds. We've made a huge difference in our cycle time for this product based on some changes that we've realized through our SOLIDWORKS Plastics tool. So hugely valuable information from this tool. Now if I run the animation on the fill, we'll see that we're still actually getting that race tracking effect, which is going to produce some weld lines still. And I'd really like to try and minimize the amount of weld lines if at all possible. So let's try another variation. I'll load up this other configuration. And with this one, basically everything is the same with the exception of my gate location. I've moved it from the lip over at the back of the part over to this edge, which is great. If we can just move the gate location and solve some of these problems, that's great. We don't have to do any changes to our part. But again, very valuable information to learn at the part design stage, that we can remedy some of these problems without changing our part design. And if we can, that's great. All right, so much better flow into this part now with that new gate location. We can try lots of other types of changes to our part. Here's one where we're changing our material. Everything else is the same, but we've changed our material from our basic Stylac material that we did before to an ABS and polycarbonate blend. And we can play around with all kinds of variations like that and really zero in on the ideal configuration for our part design. One thing that we have in this study is a pack tab, and that's going into the next level of SOLIDWORKS Plastics called SOLIDWORKS Premium currently. For 2015, this will be the professional version, but for now it's the SOLIDWORKS Plastics Premium. So let's take a look at what we can do with the Premium package. Now this one's geared a little bit more towards mold designers and mold makers. We can simulate the packing stages as well as the filling stage that we saw from the professional level. So we get everything that we get from the professional level in the Premium version, but now we can simulate packing, I should say, and a number of other things. So let's just take a look at this packing results. We're really just setting up some parameters for packing. Things like the hold pressure time and the cooling time. Once we set that up and run, we get our results. And instead of just having the flow tab in our results, we get the pack tab, which gives us 11 new reports. Things like central temperature at end of pack, and average temperature, and central temperature at post-filling end, pressure at end of packing. So again, this is very valuable information to learn, especially as a mold designer, and it's a lot more accurate. Residual stress at post-filling end, very important information to see where our high levels of stress are within the plastic after it's cooled. We can also look at volumetric shrinkage at the end of packing, and this is going to be a much more accurate calculation for our shrink at the end of our stage over what we have under the flow, because we do have volumetric shrinkage at end of fill for our flow calculation, which doesn't take into account packing. And with this one, you can see that we're up at over 11% shrinkage in some areas, down at 8 to 9% in a large area of the rest of the part. But once we pack it, then you can see that we get a much more even and lower amount of shrinkage. So we're really around in the 2%, 1.5% to 2% range for most things. Some things getting up into the 2 to 2.5% range, but really generally down in that 1.5% to 2% shrinkage range with this material. So that's a pretty dramatic improvement in the amount of shrinkage that we'll see and the accuracy in that calculation. So another thing that we can see with SOLIDWORKS Premium over the professional version is that we can see multi-cavity mold layouts. We can analyze these multi-cavity mold layouts and actually do some optimization. So let's take a look at what that looks like. I have another configuration in this part called Family Mold Layout. And this configuration has 2 of our covers and 2 of the bases for this smoke alarm that we'd want to run in one shot through a mold. Just in terms of efficiency, this is going to be a much better way to go. Just, you know, it's the same plastic mix, so it gets the same density, same mechanical properties, and same color, same surface appearance. Lots of good advantages to having everything all in one run. And what you'll see is that we can simulate the runners that run up to each one of these parts. This will simulate our fill into each one of those parts, the same as it did for the one. And in this case, what you'll see is that our covers fill a good bit before our base, which is maybe not an ideal situation, and we'll want to try and correct that. But we still get all of our data. We get pressure in the fill is just a little bit over 100, so we're a little bit over our maximum. We have our cooling time is in the same ballpark as what we had before, a little over 20 seconds. So we still get all of this really good data in terms of is this going to fill, and what are my results from the fill. But it's a little troubling that we're not filling at the same time, and that's going to have some impacts, because if we don't fill these all at the same time, that's going to affect how much pressure they're going to get, how much they'll be affected by packing, lots of things that will not be beneficial, because they'll maybe shrink different, warp different. We really want to try and balance these so that they're going to fill about the same time, and a lot of that is just going to be done with our runner size. We can do this manually. We have under Mesh, we have channel design that I could open up and see the different channel sizes, and I could try to tweak these numbers and rerun it, see how that's going to fill, and try and balance it that way. I even have a runner wizard that will allow me, just help me to go through that process, although it's still not going to help me iterate into the right size. To do that, we have runner balancing, and that's really what this tool is all about, is iterating on some parameters until we balance the fill between all 4 of our parts. We set up some parameters, we start it, and it will iterate through and find the balance between these. And I'm going to just switch to another layout that's had this already done. And take a look at the results. So with the runner balancing, it's actually going to go through and iterate on different sizes for different stretches of the runners until it meets the criteria for the fill. And it will be very close to filling at really the same time. You can see when I zoom in on the runners, they definitely have different diameters to those runners, and that's what's happened with the runner balancing. And now if I do the fill operation, you'll see that they're really filling very close to the same amount of time. Where I was off maybe 15% on the first one, about 0.2 of a second, which is pretty large for a 2-second run. On this one, they should really be filling very close to the same. And they're within less than 1/10 of a second apart now. So it's a lot closer. Runner balancing can really help save a lot of time. This can be a very painful and iterative process if you're doing it on a physical mold, and can be very, not just time consuming, but very costly. If we look at some other things in the plastics premium package, we have determining maximum injection pressure requirements. We have the ability to do insert overmolding if we have, for molding a connector and we want to have those connector pins in there to mold around it, or if we have inserted nuts in there, we can do that. We can have multiple bodies with different materials and simulate the overmolding process. We can also do a two-shot or co-molded two-shot molding process where we have 2 different materials, 2 different locations, and then 2 different times for that injection. We can do some gas-assisted injection and some gate valves. So very complete in terms of what it can do with the plastics premium package. The newest addition to the package, though, is the SOLIDWORKS Plastics Advanced. And this one shows us both warping and cooling. So let's go back and take a look at what this can do for us with another model. So with our advanced product, we can do both warp calculations and we can simulate a cooling system. With our previous packages with Pro and Premium, it's making an assumption. It's basically assuming that all the cooling is uniform across our mold, which hopefully works for most of the things, but for complex geometries, this is not a great, not really a great assumption to make. But let's go to another configuration and look at warp settings and warp results. This is going to give us a much more accurate calculation for the amount of shrinkage, and not just shrinkage, but also twist in terms of how this is going to warp when it's coming out of the mold. So once this loads up, we can go to the Plastics tab and take a look at the settings. Again, the settings are quite straightforward. You don't have to be a PhD to understand how to set this up. We have warp settings, which is just going to tell us what's our outside ambient temperature and a direction for gravity. And once we do that, we get some really nice warp results in terms of how much this is going to shrink, how much it's going to twist. We can bounce up the scale and see how much this is warping and twisting, or dial it back down to a 1 scale, which is going to be a true deformation of this part. You can see that the black lines is the original part location, and then my colored model is how much it's warped. And we can see that, you know, it's around 1 millimeter. So again, hopefully you've taken into account the shrinkage for this model and the design using our mold tools scale feature. It's pretty easy to do, and just increase the size of your part so that it accommodates for that shrink. All right, the other thing that we can do with this is we can look at our cooling system. So with cooling, what we'll do is draw some sketches for our part. Let me just go back to my original configuration and see the sketches that we've drawn. So it gives us the ability to set up a cooling system based on some sketches. And the way we're going to do this is with our meshing. We'll do a solid mesh in this case, and all we have to do is turn on cooling, and then we have the ability to turn on our virtual mold, set some parameters in terms of what sketches are my cooling runs and which ones, and then what size is my mold. It will mesh it, and then we'll get a much more accurate analysis of cooling and of warping and basically every other report that we have in there. Now you can see it's actually filled up these sketches automatically, and we're able to set things as either a cooling tube or a baffle. So I have some pieces that I would consider a baffle, and I would just choose baffle in that case and hit apply. We have some cooling tubes that come in and come in one area and exit the other, and then on the other side we have just some loops that come in and out and then out, and one that goes through. So we have lots of different ways that we could set up our cooling. I'll click next, and then the next thing that we want to do is just size our mold. So we can just put in, if we know our mold size, put in some values for the mold size, and it's going to create a virtual mold that we can then mesh and be as part of our calculation. And that's really the extent of the setup. The rest of it's pretty straightforward. We'll go back to our configuration that has the finished results and look at the results from a cooling and warping SOLIDWORKS Plastics Advanced analysis. But basically, if we compare results from an accurate mold temperature with a cooling system versus one done without SOLIDWORKS Advanced, for material above 90 degrees C, pretty close. We see some areas where it's a little bit greater extent to that temperature over in my accurate mold. Temperature at end of cooling is going to be a lot more accurate, showing hot spots in bigger regions of my part, and this is going to be valuable information to know. It's going to be a lot more accurate than with just uniform mold temperature being shown. Part warpage is going to be a lot more accurate with Plastics Advanced, doing the warp calculation, and again, when we put in a cooling system, everything becomes much more accurate for these types of calculations. We can see that we get, not an insignificant amount of difference in our shrinkage. If we go back to our part and load up these cool results, we can analyze our part on a body-by-body basis and see temperatures on our parts, on our cooling tubes, lots of things that we can see with a cooling analysis in this product. So there's temperature at end of cooling. You can see my buttons up at the in the command manager. I can turn off the cavity and I can see just the temperature of the tubes at the end of cooling. Or I could turn off the tubes and look at just my part. So cycle average temperature, part cooling time, much more accurate. Warp is going to be accurate.